So second part of 7.2. So we're still solving systems by elimination. And like I said, we'll talk about graphs and applications. Yes? The final is 20% of the total grade. All right, so on Monday, yesterday, we said that when we solve two variable systems, we can get the systems that we solve. Most of them we solve, we come up with an answer. So there are three possibilities when we solve a system of equations. We can have the way we usually want things to turn out is we have one solution. So we have two equations, x and y. We solve for x, solve for y. Check it out, everything works, and we have a nice solution to our system. So that's one of our possibilities. We can have no solutions, and that's like the example we did here, where we end up with 0 equals 120, which can never be true. So there's no solutions. And our third possibility is we could have infinite solutions. So let's take a look at if we have these three possibilities, what do the graphs of these three possibilities look like? So if we have one solution, if we have a couple of equations, 2x plus 3y equals 5 and x minus y equals 2, what are the graphs of those equations look like? We have something like x plus y equals 2. If we graph that, what is it going to look like? It's a line, right? So anything where we just have an x and y, we can solve it for y. Our highest power is 1, so we put it in y equals mx plus b form, slope-intercept form, and we end up with a line. So any of these equations where we have just a first power on x, first power on y, no exponents, we end up with lines. So for the first case, we end up with a graph, and I'm just going to draw my x and y axis, just make a sketch here. So if this is my x and y axis, this is x and y, we're not going to be really fancy here, and we graph a system of equations and we have one solution, what we end up with is two lines that just cross in one point. So where the graphs intersect is our one solution. So this is what our graphs are going to look like, something like this if we have one solution. We have two lines and they cross in one point. So this is what our first case looks like. Our second case, let's draw a quick sketch of that. So our x and our y axis like this again. So that's y and that's x. If we have no solutions, what we end up with, anybody know no solutions, what the graph looks like for no solutions?
Parallel lines.
Parallel lines. Our graphs are lines that look like this. They never meet. They're parallel. So if we solved our equations for no solutions, we end up with, if we simplify them, we end up with two lines with the same slope. So I'm just going to erase this because we were just... So our lines are parallel. They have the same slope. So if we simplified our equations, we would have two lines with the same slope. They'd be parallel. And they don't necessarily have to go this way. They could go any direction. They just never meet. So the second case, when we have no solutions, we end up with parallel lines. In our third case, if we have infinite solutions, do we know what happens then? The lines are equal. They end up being right on top of each other. So I have one line like so, and another line, I'll do it in another color, and I'll just put it right on top here. Another line like so. And we have basically the same line. So, and this is our one solution, this is our no solution case. And this is our infinite solution case. So our lines end up on top of each other. So if we simplified our equations, our system of equations, we could simplify them so the two equations looked exactly the same. So this is what our three cases for our possibilities of solutions look like. When we have one solution, we're looking where our lines cross in exactly one place. When we end up with no solutions, 0 equals 120 like we did before, we have parallel lines, they have the same slope. And if we have infinite solutions, we have the same line. For the infinite solution case, the solution is any point, any set of points on the line. So any place that's on that line is going to be a solution. That's how we end up with infinite solutions. Is we can keep going this way, we can keep going the other way, and any of those points on that line are going to be a solution. We call our case where we have when our system of equations has at least one solution, we call our equations consistent. So just so we know what the terminology means. Is everybody good with the graphs and what they mean for our systems? So our systems, when we have at least one solution, our system is consistent. And if we have no solutions, we say our system is inconsistent. And again, no solutions, we end up with something like 0 equals 1, 11 equals 120, something that's impossible. And if we have an infinite number of solutions, we end up with something like 0 equals 0, 1 equals 1, 100 equals 100, something that's true all the time. That's what tells us we have infinite number of solutions. All right, questions on the graphs and what they tell us about our system of equations? Okay, I just want to, for the last part of today's lesson, what I want to do is just do several examples of application problems that involve systems of equations. So just a couple of examples of setting up these application problems. So, and applications tend to be our favorite types of problems. Okay, so I'm just going to do a couple of examples of setting these up. So for my first example, for this example, we know that, so we have a man in a rowboat. He can row downstream, you can row 8 miles downstream in 1 hour. And this person can row 6 miles upstream, same person, in 3 hours. So it's a lot harder to row upstream. And we want to know how fast does this person row in still water. That's our first question. And how fast is the current? So these are the two questions, two things that we're trying to answer with these, with this problem. So what are we going to need to do to set this up? Anybody have an idea? What are our variables going to be? We need to pick our variables. I'll say R. Let's do R. R equals how fast this person rows. And I'm going to call it the rowing rate. So we'll say in miles per hour. So this is R is how fast a person can row. And let's call C equals the rate of the current. And this is also going to be in miles per hour. So those are our variables. Those are the things we're trying to find. The rowing rate and the rate of the current. So the way I would set this one up is we know we have a formula that we've used a lot over the years. How are distance, rate, and time related? Distance equals rate times time. So we're going to use this formula. Distance equals rate times time. So let's set up, I'm going to set up a little chart for this problem. Downstream. What is the person's total rate going downstream? If he can row at R miles per hour and the current's going C miles per hour, what's his rate going downstream? Well, his rate is 8 miles per hour. How can we write that in terms of our formula, our variables? We know it's 8 miles per hour, but in terms of our variables, what's his rate going to be going downstream? If I can row at 2 miles an hour and the current's 1 mile an hour, how fast can I go? If I'm on a traveling walkway in the airport and I walk at 2 miles an hour and the walkway goes forward at 1 mile an hour, when I'm on the walkway, how fast am I going? 3 miles an hour. I add the two, right? So downstream, my rate is how fast the person's rowing plus how fast the current's going. I add the two together. The current helps me go downstream. My time is 1 hour, and the distance is 8 miles. Upstream. What is my rate upstream if I'm rowing at some rate and the current's going against me? R minus C. The current is slowing me down. And going upstream, the problem tells us that our time is 3 hours and the distance is 6 miles. So I'm going to use this formula, distance equals rate times time, to set up my two equations. Here I have a distance, a rate, and a time for downstream, a distance, a rate, and a time for upstream. So my equations are going to be the distance, 8, equals the rate, r plus c, times my time, times 1. I'm just using distance equals rate times time. And for, that's going up downstream. Going upstream, my distance, 6, equals the rate, r minus c, times 3. So that's my system of equations. So I can rewrite this as, I'm just going to rewrite it and rearrange it. R plus C equals 8 from this one. And from this one, I'm going to distribute the 3. So 3R minus 3C equals 6. So now I have a system of equations, two variables, and I can solve this using elimination. So these are my equations, my system. So to solve this system, what are we going to want to do? What's going to make this easy? Multiply the top by 3. So multiply by 3. I'm going to write that out here in the margin. So multiply this one by 3. So I get 3R minus 3C equals 24. For the bottom one, I have 3R, I guess this should be plus, sorry, 3R plus 3C. 3R minus 3C equals 6. So that's my new system. Add those together, and I get 6R equals 30. Divide by 6, so R equals 5. Plug that into my equation here, and I get that C equals 3. So the person can row at 5 miles an hour, and the current is going at 3 miles an hour. So on any of these application problems, and they're all going to be more or less the same, we need to pick our variables, and then we have to figure out how we can write some kind of equation with those two variables. Anytime we have a distance, a rate having to do with miles an hour and distance, you're going to want to use, most likely you're going to want to use distance equals rate times time to set up your equations. And setting up a nice little chart like this helps you keep things organized. Questions on that problem? All right, let's do one more. This one has to do with investments. All right, so in this problem, we have $10,000 to invest. $10,000, and we're just earning simple interest. So we just get some percentage of our money after a certain amount of time. So we have simple interest. So we're not dealing with any kind of special compounding or anything. So we have about $10,000. One account, we're going to invest in two accounts. One pays 8%, and the other pays 6%. We want to figure out how much to invest in each. to earn $720. So we want to earn $720 in interest on this investment. So to set this one up, we need variables, and then we need our equations. So how do we want to, what do we want to call our variables? How are we going to set our variables up? Anybody have an idea? What would we like to call our variables? How about x and y? Let's let x be the amount that we put in the 8% interest. X equals the amount at 8%, and let's let y equal the amount at 6%. What kind of relationship, what kind of equation can we write between x and y? What's the total that we have to invest? What's the problem? Tell us the total that we have to invest. $10,000? X plus y. The amount that so we're splitting our investment up. So this is a certain amount of money. This is a certain amount of money. So if we add it all together, it has to equal $10,000. So no matter how we split it up, if we add it back together, we end up with $10,000. The problem tells us that the one is going to pay us 8% interest, the other pays 6% interest, and we want the total to be $720. So 8% as a decimal. How do I write 8% as a decimal? 0.08 times however much I invest in that account, plus the 6% interest as a decimal, 0.06. Y, this is how much I earn in the 8% account, 0.08 times however much I invest in there, plus 0.06, that's how much I'm going to earn in the other account. We want that total investment to give us $720. So there are my equations. The total amount I have to invest is $10,000. The amount I earn in one account plus the amount I earn in the other account has to add up to $720. So now we have our variables, we have our equations. So how are we going to go about solving this system? What do we want to do? Multiply the bottom by 100. Okay, so we're going to multiply this by, multiply the bottom by 100. So I get, my system then turns into x plus y equals 10,000 and 8x plus 6y equals, and we multiply 720 by 100, and I get 7,200. Not 7,200, 72,000. So that becomes our new system. Now what do we want to do to this system to solve this? Times, okay, which would you like to do? Times -8. Okay, works for me. So we're multiplying the top by -8. So then my new system becomes -8x minus 8y equals minus 80,000. And on the bottom I have 8x plus 6y equals 72,000. Add those together. This adds to 0. I get negative 2y equals negative 8,000. Divide by negative 2 and y comes out to be 4,000. Plug that back into this equation, and that tells me that x has to equal $6,000. So I plug that back into this first equation, and x has to equal $6,000. So my investment, $6,000 at 8%, $4,000 at 6%, and that'll give me $720 in interest. So all the application problems are some variation of one of these two types of problems. There's either going to be a rate, or there's going to be some kind of mixture like this, where we have to add two numbers up to equal the total, and then the amount of one plus the amount of other equals the amount in the mixture. So the interest problem and the mixture problem are essentially the same, and then our rate problems usually involve distance equals rate times time. So any questions on the applications examples? Okay. Our homework. There you go.